So hello, very good evening to the students who have joined, and can you just let me know in the chat box if my voice is clear and the screen is visible to you? Is the presentation visible to you, and can you hear my voice clearly? Please write in the chat box. Okay, fine. We will wait for 5 minutes and then we will start today's session. So very good evening. So there might be some problems due to internet connections today also, like last day. So I want every student to be in the class, even if my connection even if I lose my internet connection, I will surely get back to you as soon as possible, but you guys don't leave the class, okay? Yeah, very good evening. So due to some internet connection, due to some bad weather, the internet connection is unstable today too. So I want all of you to be present in the class, even if my connection is broken, because I will just rejoin soon. uh, so don't worry about it, but don't leave the class, okay? We will wait for 5 minutes and then we will just start. Okay, so I think we should start. Eventually, when other students will join, I will add them, okay, automatically. So, very good evening to the students who have joined today's session. My name is Moshumi Dev and I am a PMRF fellow from the Department of Chemistry and Chemical Biology, IIT ISM Dhanbad. today it is the week 9 live session for the NPTEL course of Medicinal Chemistry. Just like every week, today also we will solve around 15 to 20 MCQs where we will discuss the week 10 course contents. Okay. After every question, I want all the students to try to answer these questions in the chat box. It is alright if the answers are wrong, but at least I think every student should try to answer the questions. Okay, that is how we will have a free fruitful class with lots of interaction. And after each and every question, if you have any doubt regarding the question or regarding the answer, also please do write in the chat box at the end of the session or in between the session. I will try to solve your doubts. Okay, and this kind of class we have every week, and today also we will start this class right now, and at the end of the class I will share this lecture PPT and the recording of today's class. So due to some internet connection we had some problem in last class, so if same kind of problem arises, I want all of you to be little patient with me and don't leave the call. I will just try to rejoin as soon as possible. Okay, so I think it is already 6 p.m. and we should start our session, and if somebody joins, I will just add them up. Okay, and if you have any problem from hearing my voice or for seeing the PPT, please do let me know. I will try to manage it. Okay, so I hope my voice is clear and you are able to see the PPT, right? So should we start? If you have any problem, if my voice is not clear or anything, please do write in the chat box. Okay, yeah, okay, very good. So I think we should start. So after every question, I want all of you to try to answer this question. Now it does not matter if the answer is correct or wrong, but if you know it, or if you do not know, if you think it is the right answer, please do write it. Okay, so our first question, the first question is, it says that, okay, so it says which of the following is the first known antibacterial agent? Your options are as follows: number A penicillin, number B ureastibamine, number C salvarsan, and number D morpholin. Okay, so among these four, the question you have to identify which of the following is the first known antibacterial agent. So we all know that what is the antibacterial agent? The agents which are the drugs which are used against the bacteria which are harmful for our body. Okay, so in our body there are also some good bacteria also which are in required by our body for various functions, but there are mostly harmful bacteria which affect our body in several ways, and these bacteria can enter our body by the means of food or the air or anything, okay, water also. So to tackle those bacteria, these antibacterial agents are used. Okay, so this following question here it has been asked that which of the following is the first known antibacterial agent, and your options are number A penicillin, number B ureastibamine, number C salvarsan, and number D morpholin. So write in the chat box which of the following you guys think is the correct answer for this question. Again I am saying it does not matter if the answer is correct or wrong, but please try. Okay, so is there any answer for this question? Okay, so we have the answers number A, number A, and number C. Okay, let us check which is the correct answer for this question. Okay, so the correct answer is number C, salvarsan. Okay, so salvarsan was the first antibacterial drug, okay, which is known as a for antibacterial. So look, let us look at the structure for the salvarsan. So this is the structure for the salvarsan. So as you can see, there are two phenyl ring, and this is a very symmetric molecule where we have two one arsenic double bond, and we have this aminophenol kind of moiety, orthoaminophenol in two sides. Okay, so this is known as the salvarsan. So salvarsan generally this has a pentameric structure. Okay, so the structure, the drug which has been given to us is generally in the pentameric form like this. All the arsenic they have tendency to form single bond more than forming a double bond. So this kind of pentameric structure has been seen for the salvarsan. So this salvarsan also is a very interesting drug because it has a very interesting element which is the arsenic. This arsenic element, we all know, in most of the time arsenic is known to have toxic effect for our bodies, but this particular drug, which is the first known antibacterial agent, also have this molecule, this element arsenic. Okay, so this was the first question of today's session, and as I have said that it does not matter if the answer is correct or wrong, but you guys trying to answer this question is very important. Okay, so this was the first question. Now I will move toward the second question. So the problem number 2, it says that which of the following is not a semi-synthetic antibacterial agent. Okay, and the options are number A, ampicillin, number B, carbonicillin, number C, cephalexin, and number D, sulfonamide. So which of the following is not a semi-synthetic antibacterial agent among these 4 options? Try to answer this question, and after you guys are done trying, we will look at the correct answer, then we will discuss a little about the semi-synthetic antibacterial agents and about these questions. So your options are number A, ampicillin, number B, carbonicillin, number C, cephalexin, and number D, sulfonamide. Which of the following is not a semi-synthetic antibacterial agent? So do we have any answer for the question number 2? Let me check. Okay, we have one D and one B. Okay. Okay, let us check the answer. So the correct answer for problem number 2 is number D, sulfonamide. Very good. So we had one correct answer. In the previous question also we had one correct answer. So see, this is very important, like you guys are responding. So let us check what is the sources of antibacterial agents. So this is the structure of sulfonamide. As you can see, sulfonamide. So amide, what is a amide? All we know, amide is a bond between a carboxylic acid and amine. So C double bond O and OH. This is a carboxylic acid, and let us say this is R. And if it is reacted with a amine, so let us write amine in this way, R dash NH2. So this there is a elimination of water. Okay, so one hydrogen for amine, one this hydroxyl group, they take part in the reaction, and we got a product which is called a amide. So what is the amide bond? There is a C double bond O, there is NH, and then there is R dash. So this C double bond O and NH, it is called the amide bond, and the amide bond, where we see amide bonds in our body, in the peptides. Okay, the protein, the peptides, there is a amide bond between the amino acids. Okay, so what is a sulfonamide then? So if there is a sulfonic acid, like this, like there is a R. Okay, somebody wants to join. Okay, so if there is a sulfonic acid present like this, like if we have in place of carboxylic acid S, double bond O, double bond O and OH. And if this reacts with a amine, then we have something which is called a sulfonamide, because it have a sulfur instead of a carbon. Okay. So, this is the structure of a general sulfonamide, and it is a synthetic antibacterial agent, and in your question it has been asked which of the following is not a semi-synthetic antibacterial agent. So, ampicillin, carbonicillin and cephalexin, these three are semi-synthetic antibacterial agent, but sulfonamide, it is a solely synthetic antibacterial agent. Okay. So, that is why it was the wrong answer. So, let us check out the sources of antibacterial agents. So, number first source, which is the natural source. Okay, natural source are mainly the fungal sources. The original antibiotics were derived from fungal sources. These can be referred to as the natural antibiotics, that is the benzyl penicillin and gentamicin are the natural antibiotics. Now, what are the semi-synthetic antibiotic? Chemically altered natural compound developed to decrease the toxicity and increase the effectiveness. For example, ampicillin and amikacin are the semi-synthetic antibiotics. So, what is the semi-synthetic antibiotic? Then in short, it is derived from natural products. So, if there is a natural product which is showing the antibacterial effect, but also when it is given as an antibacterial, it produces some toxicity in our body. So, to remove the toxicity, that natural product or the naturally occurring agent are needed to be modified, and when this is modified a little bit, it is called a semi-synthetic, means it is not a completely synthetic, it is derived from natural product, but we are modifying it to reduce the toxicity. So, these are called the semi-synthetic antibiotic. And the last or not the least is the chemically designed in lab. The bacteria are not exposed to this compound until they are released. They are also designed to have a greater effectiveness and less toxicity. And so, synthetic antibiotics are those which are not found in nature, okay, or they do not have any connection for nature, but they are solely chemically synthesized in the lab. So, the examples are like sulfonamide, moxifloxacin, norfloxacin, these are the synthetic antibiotic. So, it is very important for you to remember what are the sources of antibacterial agents, the natural sources, and what are the example of natural antibacterial agents, then the semi-synthetic ones, what are those, and what is the what are the examples of semi-synthetic, and also the synthetic ones. Okay, what are the sources of synthetic antibacterial and what is the examples. So, this is the thing about the question number 2. So, I think it is clear. Again I am saying, if you have any doubt, anything, any query, please do write in the chat box at the end of the session or in between when I am checking out your answers. I will try to answer your queries. Okay. And also, if due to some reason my internet connection got disrupted, do not leave the class, I will rejoin soon. Okay. So, do not worry, these videos and all those PPTs will be shared to you in due time. So, now we will just look at the question number 3. So, problem number 3 says that solid phase synthesis is frequently used in combinatorial chemistry. What is meant by solid phase synthesis? Your options are number A, reactions are carried out without solvent. Number B, reagents and reactants are attached to a solid phase support. Number C, reagents are used in a solid phase. Number D, molecules are constructed on a solid phase support. So, the solid phase synthesis is a very important thing, and there are many places in chemistry where we use the solid phase synthesis, and you have to identify what is meant by the solid phase synthesis. Your options are number A, reactions are carried out without solvent. Number B, reagents and reactants are attached to a solid phase support. Number C, reagents are used in a solid phase. Number D, molecules are constructed on a solid phase support. So, again I want all of the students who are present in the class, please write in the chat box which of the following options you think is the correct answer for this question, and it does not matter if your answer is wrong, but you are trying to answer the question is very important. Okay. So, take 1 minute and read all the options very carefully and write which of the following options you think is the correct one. So, do we have any answer for question number 3? As I said, okay, so I think up to this we had, so D, B and D. So, we have either D or B for answer of this questions. Okay, so let us check what is the correct answer. So, the correct answer is number D, molecules are constructed on a solid phase support. Okay. So, let us now check what is a solid phase synthesis. So, combinatorial synthesis, I will use a laser pointer. So, combinatorial synthesis is based on solid phase chemistry. It uses filtration as a separation and purification technique. It is easy to removal the easy removal of unwanted substance by a simple filtration is the core of the library synthesis. In this synthesis, substituted resin bits are used as a solid phase, which is actually a gel-like matrix of connected polymeric molecule distended by the axis of the solvent molecules. Okay. So, as you can see, this is the for example of the picture of the solid phase synthesis. Now, what is the resin beds? The use of the solid support for organic synthesis requires a cross-linked insoluble but solvent swellable polymeric material that is inert to the conditions of the synthesis. Some means of linking the substrate to the solid support that permits selective cleavage of the product from the solid support during the synthesis. A synthetic procedure compatible with the linker and the solid. So, this is all about the solid phase synthesis. We will actually have a more detail, I think, in coming weeks also about the solid phase synthesis. So, just remember, in the solid phase synthesis the molecules are actually constructed on a solid phase support, which is actually a polymeric resin bed which have a gel like substance, okay, and it is very easy to remove the unwanted substrate by simple filtration, and that is why this is very is a heart or core of the library synthesis. Okay. So, this was the problem number 3. Now, I will move toward the problem number 4. So, problem number 4, it says that what is the mechanism of action of the tetracyclines. So, as tetracyclines are a very important class of the antibacterial agents, and now you have to identify which is the mechanism of action of this important antibacterial agents. Okay. Number A, prevention of bacterial DNA synthesis. Number B, prevention of bacterial protein synthesis. Number C, prevention of bacterial cell wall synthesis, and number D, prevention of bacterial RNA synthesis. And please identify the correct mechanism of action of tetracyclines. I want every student present in the class to try to answer this question. Once you are done trying, we will look up the what is the correct answer, and we will discuss in detail what are the tetracycline, what is the examples of the tetracycline molecules, and what is the mechanism of action, all in the detail. But before that, I want you to try to answer this question. Okay, so let me check if there are any correct or any answer for the question. Okay, so I think A and B are the answers till now. Okay, let us check what is the correct answer. So, the correct answer for problem number 4 is number B, prevention of bacterial protein synthesis. So, tetracyclines, okay, let me just use the laser pointer. So, mechanism of action for tetracyclines. Tetracyclines enter the susceptible organisms via passive diffusion and by an energy dependent transport protein mechanism unique to the bacterial inner cytoplasmic membrane. Tetracyclines concentrate intercellularly in susceptible organisms. The drugs bind reversibly to the 30S subunit of the bacterial ribosome. This action prevents the binding of tRNA to the mRNA ribosome complex, thereby inhibiting bacterial protein synthesis. So, as you can see, this is your bacterial ribosome, and as we have I think read in last to last class, I do not remember exactly, but we have read it that this bacterial or the this bacterial ribosome, it has this two subunit, 50S subunit and 30S subunit, and this is the prokaryotic ribosome, and for the eukaryotic ribosome we have I think 60S or and 40S ribosome. Okay. So, as you can see in this ribosome there is a P site and there is a A site. So, in this A site actually the tRNA binds, okay, and this is the mRNA template, okay, and here the tRNA binds and gives the tRNA, it actually transfers the which is called the amino acid, and the protein synthesis happen like this nascent polypeptide chain. But in this phase what is the, which is called the A site of the ribosome, where tRNA actually binds, the tetracycline molecules, they actually start binding to this place. So, if there is a tetracycline molecule which is binded to with the place of the A site, then the tRNA won't be able to come and bind here. So, that is how the protein synthesis is actually inhibited, and if there is no protein synthesis, then what will happen, the antibacterial molecule, the bacteria molecule, it will not survive without the protein. So, that is how this tetracycline molecules are imparting their antibacterial action. Okay. So, to remember, the mechanism of action of tetracyclines is the prevention of the bacterial protein synthesis. Okay. So, I hope the question, the answer, this is clear to all. Again I am saying, at any point of the class, if you have any doubt or anything, please do write in the chat box, okay. At the end of the session or in between when I am checking out your answers, I will try to answer those doubts, but I want all the students at least try answering the question, otherwise we will not have any fruitful result out of this class. Okay. So, now I will move toward the next problem. So, problem number 5, it says which of the following terms refers to the molecular modeling computational method that uses equations obeying the laws of the classical physics. The options are quantum mechanics, number B molecular mechanics, number C molecular calculations, and number D quantum theory. So, which of the following terms refer to the molecular modeling computational method that uses equations obeying the laws of classical physics? Read the question carefully, then read the answers carefully, and everybody try to answer this question in the chat box. Which of the following terms refer to the molecular modeling computational method that uses equations obeying the laws of the classical physics? Is it quantum mechanics, molecular calculations, or quantum theory? Everybody try to answer this question in the chat box. Let me check if there is any answer for it. Okay, number C and number B. Okay, let us check. Okay, so the correct answer for problem number 5 is number B, molecular mechanics. So, what is molecular mechanics? So, molecular mechanics is a computational method that computes the potential energy surface for a particular arrangement of atoms using potential functions that are derived using classical physics. Molecular mechanics or force field methods ignores the electronic motions and calculate the potential energy of a system as a function of nuclear position only. Okay. So, what is the difference between the quantum mechanics and molecular mechanics, which is very important topic. So, quantum mechanics classical laws fail at the quantum limit. Okay. Now, where does the electron go, what does the electron do? So, this can be done by the quantum mechanics, solves for the Schrodinger equation H psi equal to E psi, and accounts for the explicit interaction of electrons, highly accurate. Okay, and molecular mechanics or classical mechanics solves for Newtonian equation of motion, which is F equal to m into A, where F is the force, m is the mass, and A is the acceleration. Atoms equal to balls, bonds are equal to springs. So, in this molecular mechanism, atoms are compared with ball and the bonds with the spring. So, no electrons and much faster compared to the quantum mechanical methods. The scaling. So, the scaling of the quantum mechanics is n to the power 4 to n to the power 5, 100 atoms equal to 1 hour, 200 atoms equal to 16 to 32 hours. But the scales for the n to the power 1 to n to the power 2, 10,000 atoms equal to 1 second and 20,000 atom equal to 2 to 4 seconds. So, this is the scaling basic, you do not need to understand in details, but remember the molecular mechanics which actually used for the molecular model in computational method that uses the equation of classical physics. Okay. So, this was your problem number 5. Now, we will move toward the problem number 6. So, problem number 6, it says that what is the most important thing needed for the molecular docking? Number A, ligand's chemical property. Number B, protein structure. Number C, protein stability, and number D, ligand stability. So, there is a method which is known as molecular docking method, and you have to identify which of the following is the most important thing needed for the molecular docking. Number A, ligand's chemical property. Number B, protein structure. Number C, protein stability, and number D, ligand stability. Okay, so do we have any answer for the question? So, we have answer, I think these are number A and number C. Okay, let us check. Okay, so the correct answer for this question is number B, protein structure. So, protein structure is the most important thing for the molecular docking, to start the docking. So, molecular docking is very important tool in SBDT, and SBDT it stands for the structure based drug design. Molecular docking aims to identify the best binding poses of a ligand in a predefined protein pocket. It also generates a docking score. The score is based on the scoring function of the algorithm and not predicted binding affinity. Docking is used to identify the scaffold from library of compound which could be a potential inhibitor of a protein to predict the binding pose of a known inhibitor in the binding pocket of a protein. So, there must be a target protein and there must be a ligand. So, all the systems should be prepared at first, then the docking calculation happen, then scored, then post processing. So, that is how the thing happens. So, what happens at first in docking, let me tell you. So, for molecular docking, first you need a target protein. Okay. So, you suppose you have a target protein and you want to design a particular inhibitor for the target protein. So, your first work will be to download the protein PDB structure, and PDB structure, by PDB structure I mean the protein data bank structure. So, if you type in the Google PDB or protein data bank, you will find there is a website where there are all the proteins which have been identified till now, which structure have been characterized by the methods of like crystallography and anything, all structure are deposited in the protein data bank. Okay. So, from the protein data bank you have to download the protein structure, and because without the protein structure you cannot start doing your molecular docking. Now, once you have downloaded the protein structure, you have to use the softwares to prepare that protein. Now, by preparing the protein, I mean to say that, see what is the protein structure, how the protein structure have been characterized. So, generally what happens, the methods of X-ray crystallography has been vastly used for the protein structure determination, and once we have a crystal of that protein particular. So, what happens when you are crystallizing a protein, there are many things which are crystallizing with the protein, like there are some heteroatom, there are water molecules, there are some ions. Okay. So, for preparing the protein, you have to delete all these things, and after deleting we have to just add some residues, delete some residues, and like that we have to prepare the protein structure at first. Then we have to design a ligand. So, as you can see, this is the ribbon structure of protein which can be downloaded and prepared from the by the websites, and this is the structure of a ligand which can be actually which can be drawn, and then we can use this structure of this protein and use the structure of this ligand, and we have to use the computational method. So, there are many softwares which we can use to do the docking. Autodoc Vina is the free software which we can use widely, and after doing the docking, what the docking does, it assumes that the protein is the protein is fixed. Okay. The protein is not changing in or doing any function or doing any rotation. The ligand can move as much as it want, and first we have to define a binding pocket, and then we have to perform the docking. So, the docking will actually give you 10 most favorable poses for the ligand, which is based on the interaction of the ligand with the particular protein site. Okay. And from based on this 10 docking poses, you have to identify which is the perfect or which is the best docking pose, and then from that we have to do the structure modification of that particular ligand. Okay. So, this was a very I have just told you very lucid way, but doing it a very little bit tricky, that it is not that much of complicated also. Okay. So, this was all about molecular docking, and it is a very important technique right now for doing the structure based drug design. Okay. So, this was all about the problem number 6. Now, I will move toward the problem number 7. So, problem number 7, it says that what term is used to describe the inhibition of two different enzymes in the same biosynthetic pathway. The options are number A, sequential blocking, number B, enzyme inhibition, number C, parallel inhibition, and number D, multi-drug therapy. So, you have to identify which of the following term is used to describe the inhibition of two different enzymes in the same biosynthetic pathway. So, if there is a biosynthetic pathway, I think let us say if there is a reaction from A to E, and there is from A to B and B to C, then from C to D and D to E, then all these steps are actually catalyzed by some enzymes, and you are inhibiting two different enzymes in same synthetic pathway. So, what does this mechanism called? Options are number A, sequential blocking, number B, enzyme inhibition, number C, parallel inhibition, and number D, multi-drug therapy. So, I want all of you to try to answer this question in the chat box. It does not matter if your answer is correct or wrong, plus please try to answer this. Okay, so are there any answers for this question? Okay, so I think number D and number C. C and number D. Okay, so we have two answers, I think number C and number D. Okay, let us check out. So the correct answer is number A, sequential blocking. Okay, so I think multi-drug therapy is something I have discussed in last class also. So in multi-drug therapy, actually we use one single compound or single drug to actually to inhibit two different targets, okay, and that is called the multi-drug therapy. So in sequential blocking, what happens, like let me just first draw it. Okay, so this sequential blocking we will also read in detail in, I think, in some later in some week. Okay, so let us say there is a biosynthetic pathway from A to D. Okay, so this pathway involves some multiple steps, like from A, first we have from A to B, then from B to we have C, and then from C to we have D. And this, all of these three steps which we have, it is catalyzed by three different enzymes, like enzyme E1, enzyme E2 and enzyme E3. Okay. So, what happens in sequential blocking? This is the method where we inhibit two different enzymes in same biosynthetic pathway. So, let us say if we only inhibit this enzyme, enzyme number E2, then this the total efficiency may not be that much, but if we can inhibit this E2 and E3 or E2 or E1 or any two of it all together simultaneously, we will have very much will be more able to inhibit this pathway, and this method is called the sequential blocking. Okay. So, this sequential blocking we will have in detail in later in some classes. Okay. And what is the enzyme inhibitors? So, in enzyme, okay, let me just erase this thing. Okay. So, there are different type of this inhibitor for the enzymes, okay, and this can be like, okay, yeah. So, as you can see, there is an enzyme we have a active site and an allosteric site, and in active site the substrate can be bind, and then if the active site the inhibitor binds, then it is called the active inhibitor. Okay, and if the inhibitor binds in the allosteric site, it is called the feedback inhibitor. Okay, so feedback inhibitor can bind in the allosteric site and can change the active site so the substrate cannot be bind, and the active inhibitors, they can itself bind to the active site of the enzymes, and they can inhibit the binding of the substrate with the enzyme. Okay. So, this is your enzyme inhibition and sequential blocking. So, now we will move toward the next problem. So, problem number 8, it says that which of the following structures shows the pharmacophore for the tetracyclines. Which of the following structure shows the pharmacophore of the tetracyclines? Which of the following heteroatoms indicated could not act as a hydrogen bond acceptor? So, as you can see, this structure, which is the active pharmacophore structure for the tetracycline. We just discussed about tetracycline in last to last question, I think. So, there are few heteroatoms are mentioned here, like heteroatom A, which is this molecule, heteroatom B, which is this nitrogen, heteroatom C, which is this oxygen, and heteroatom D is this oxygen. So, you have to identify which of the following heteroatom cannot act as a hydrogen bond acceptor. Okay. So, your options are heteroatom A, then number B heteroatom B, then number C heteroatom C, and number D heteroatom D. So, identify which of the following cannot act as a hydrogen bond acceptor. I think somebody wants to join. Okay, I want everybody to try to answer this question. This is very easy question. Okay, which of the following heteroatom could not act as a hydrogen bond acceptor? Look at the carefully all the atoms which are mentioned, number A, B, C and D, then identify which of the following cannot act as a hydrogen bond acceptor. Okay, let me check if there are any answers for this question. Okay, number B, number B, number B. Okay, so number B are the is the most used answer. Okay, let me check. So the correct answer is very good, number B. So number B heteroatom, it could not act as a hydrogen bond acceptor. Now what is a hydrogen bond acceptor and what is a hydrogen bond donor? So hydrogen bond donor, that is a hydrogen bond donor is a chemical compound which contains proton to be donated, and hydrogen bond acceptor is the chemical compound which contains a lone pair of electrons which participate in the hydrogen bond formation. The hydrogen bond donor must contain hydrogen atoms directly bound to the compound via covalent bond, and this must contain more electronegative atoms such as oxygen, nitrogen and fluorine, which contain lone pair of electrons. It donates proton and it attracts proton. Okay, so these are the examples for hydrogen bond donor and acceptors. So as you can see, if there is a NH2 and there is a OH, so these are the hydrogen bond donors, because there are hydrogens which is attached to electronegative atoms like oxygen and nitrogen. So it can be easily donated toward a hydrogen bond. Hydrogen bond acceptors are like this ketone group, this O ether group, this aldehyde is aldehydic ketonic carbonyl carbon, and the carbonyl carbons of the esters. So these oxygens have a lone pair of electrons which can act to attract hydrogens and can form hydrogen bond. So which is the example of both this kind of amide, look, let me use the laser pointer. So this kind of amides which have also a ketonic group and NH2. So this can be seen as both this kind of acid and this kind of molecules can act as a both hydrogen bond donor acceptor, but this kind of molecule which cannot be used as neither hydrogen atom hydrogen bond donor nor a hydrogen bond acceptor. Okay, so I think this is comparatively easy question and all of you have given right answer. Okay. Now I will move toward the next problem. So problem number 9, it says that which of the following is the general mechanism of action for the vancomycin? Number A, inhibition of metabolic enzyme. Number B, inhibition of cell wall synthesis. Number C, disruption of protein synthesis. Number D, inhibition of nucleic acid transcription and replication. So there is another very important antibiotic which is known as the vancomycin, and you have to identify which is the general mechanism of action or method of action for the antibacterial effect of the vancomycin. The options are number A, inhibition of metabolic enzymes, number B, inhibition of cell wall synthesis, number C, disruption of protein synthesis, number D, inhibition of the nucleic acid transcription and replication. Which of the following is the general mechanism of action of vancomycin? Okay, let me check if there is any answers for this question. So have you guys tried? Okay, so number B, number D, number C. Okay, so now we have 3 different answers, which is very interesting. Okay, so we have number B, C and D, 3 options. Okay, let us check out what is the correct answer. So the correct answer is number B, inhibition of cell wall synthesis. Okay, so this is the structure of a vancomycin, and this kind of molecules are called macrocyclic molecules. So as you can see, this is a very huge structure. Okay, there are so many bonds, so many atoms, and very obviously these molecules do not follow the Lipinski's rule of 5, because these molecules molecular weight is more than 500. So this was I think I have discussed, like this was a exception for that Lipinski's rule of 5. Okay, so vancomycin, as you can see, this is the structure, it is shown very in short manner. So this vancomycin actually inhibits the cell wall synthesis of the bacteria. Okay, and it disrupts the membrane integrity of the bacterial cell wall, and by doing this it actually inhibits it actually disrupts the bacterial cell wall synthesis and eventually killing the bacterial cells. Okay, so this is the mechanism of action for the vancomycin, the inhibition of the cell wall synthesis of the bacteria. Okay. So the detailed mechanism you need not to know right now what is the detailed mechanism for the cell wall inhibition, but just remember what is the I mean just in broader sense, just remember what is the mechanism of action, the inhibition of the cell wall biosynthesis. Okay, and the disruption of the membrane integrity. So now I will move toward the next problem. So problem number 10, it says that what reaction is catalyzed by beta lactamase inhibition enzyme. Okay, the number A, the final cross linking reaction to form bacterial cell wall. Number B, the hydrolysis of the acyl side chain from the penicillin structures. Number C, hydrolysis of the 4-member ring present in the penicillin. And number D, the biosynthesis of penicillin structure from amino acids valine and cysteine. So beta lactamase is a important enzyme, and this actually present in the bacteria. Okay, and this beta lactamase enzymes actually a very important drug target for designing the antibacterial agents. Many antibacterial agents are this beta lactamase enzyme inhibitors. Okay, now you have to identify which of the following reactions is catalyzed by this beta lactamase enzyme. The options are number A, final cross-linking reaction to form the bacterial cell wall. Number B, the hydrolysis of the acyl side chain from the penicillin structures. Number C, the hydrolysis of the 4-membered ring present in the penicillin. Number D, the biosynthesis of the penicillin structure from the amino acids valine and cysteine. Everybody try to answer this question in the chat box. As usual, as I always say, it does not matter if the answer is wrong or right, but whoever is present in the class, everybody should try to answer this. Okay, so are there any answers for this question? Okay, yeah, okay, I will show you the hydrogen bond donor acceptance slide again, okay, don't worry. So I think these are the answers for the question number C, number D. Okay, let us actually solve this question at first, then we will check out the hydrogen bond donor acceptance slide again, okay. Okay, so let us see what is the correct answer. The correct answer is yes, number C, the hydrolysis of the 4-membered ring present in the penicillin. This is the reaction which is catalyzed by the beta lactamase enzyme, okay. So, this is a ring which is called the beta lactam ring. So, as you can see, what is the lactam? And lactam is nothing but a cyclic amide, okay. And if the cyclic amide, it is the beta lactamase, because there are 2 carbons present. This is the alpha carbon and this is the beta carbon, okay. So, since this is a cyclic lactam has this only 2 carbon alpha beta, it is called the beta lactam ring, okay. So, this is the structure of the penicillin. Okay, so as you can see, there is a beta lactam ring present in the penicillin, and what does this beta lactamase enzyme do? It actually hydrolyzes this beta lactam ring in the penicillin, okay. And that's, as I said, penicillin, as we all know, is a very important antibacterial agent, right. So, if this beta lactamase enzyme which is present in the bacteria, it can hydrolyze this penicillin ring easily, okay. So, this beta lactamase inhibitors are also a very good drug target for the antibacterial agents, and this is the actually mechanism of action, how this beta lactamase is this penicillin reacts with the cell wall. So, as you can see, there is a glutamate here, there is a lysine here, and there is a serine here, okay. This is called the serine beta lactamase, and that is how the reaction happens. First, there is a water mediated base at first this base abstracts this proton of the serine, and this oxygen attacks to this carbonyl carbon of beta lactam ring, and the ring opens, okay. And then there is another base which is this glutamate, and then it takes up a hydrogen for a water molecule and this hydroxyl, and that is how the hydrolysis of the beta lactam ring happens, okay. And this is the example of metallo beta lactamase, okay. That is how there is a zinc, and this zinc actually forms in this beta lactamase enzyme. There is a zinc which is here, there is a OH present here, and this OH attacks this beta lactam ring, and we have this metallo beta lactamase formation, okay. So, and we have somebody has asked to just repeat the question number. So, okay, let me check where was the question. Okay, this one is the slide for the hydrogen bond donor and hydrogen bond acceptor. Okay, so is there any question which particular question which you want to ask from this slide? Did you understand what is the hydrogen bond donor, what is the hydrogen bond acceptor, and the examples for the both, or should I repeat anything here? So, do you have any question from this slide? If yes, you can write in the chat box, okay. I will just answer the question. So, I think it is clear to all what is the hydrogen bond donor and what is the hydrogen bond example, hydrogen bond acceptor, and what are the examples. Got it, okay, very good. So, okay. So, this was the number, I think, hydrogen bond donor acceptor, and so now we have completed 10th question, okay. So, like every day I will give you a short break, but before going to the break, we will look at the question number 11, okay. So, let us first check the question number 11. So, question number 11, it says that which of the following diagram has the correct numbering system for the fluoroquinolones. Fluoroquinolones are also a very important class of the antibacterial agent, and the main structure or the pharmacophoric structure is this of this fluoroquinolone, and as you can see, there are numberings at each and every carbon for the fluoroquinolones, and you have to identify which of the following is the correct numbering system for the fluoroquinolone. Option A, B, C, or number D. Okay. So, now I am giving you a break of about 2 to 3 minutes, okay. So, I am not leaving the class, I will just off my camera and the microphone. You just look at the structures carefully, and what is the correct answer you think, you write in the chat box. After 2 to 3 minutes at sharp 7 p.m. I will rejoin, and I will check the answer, and then we will discuss the problem number 11, okay. I am not leaving, I am just keeping my camera and the microphone off, but you guys try to answer this question, okay. Okay, hello. So I am back. So is my voice audible? Is everybody present in the class? Yeah. Okay, very good. So I think we have answers like number A and number D. Okay, okay. Okay, very good. So let us check out what is the correct answer. Okay, so the correct answer is number A. Okay, so number A is the correct numbering for the fluoroquinolones. So this is the examples of the fluoroquinolones. Okay. First we will see it. So as you can see, this is the structure of fluoroquinolone, and we start doing numbering from this nitrogen. Okay, so whenever there is a this kind of the polyhydrocarbons, so we start the numbering from the heteroatoms when if the heteroatom is present. So we will start numbering from the nitrogen, and once there is a when we then we do this as gradually. Okay, so there should not be any break, and the ring junctions should be numbered at last, or it may not be numbered at every time. So if you start with this nitrogen, then 1 2 3 4 5 6 7 and 8. So this is the correct way of numbering this fluoroquinolones, and these are the examples of the fluoroquinolones. Okay, and this is the generic fluoroquinolone structure, and the examples are like nalidixic acid, pefloxacin, ciprofloxacin, citalfloxacin, moxifloxacin, levofloxacin. So if there is a this term oxacin, okay, like ciprofloxacin, and we, as you can see, there is this term oxacin in at every after every drug. Okay, if there is this term present, then you have to remember this is just example for the fluoroquinolones. Okay, and you can actually give a name for a drug like say moxifloxacin, and you can be asked which is the class of the compound which it belongs to, then you remember it is the fluoroquinolones. So as you can see, this is the generic structure for the fluoroquinolone, right? There are two phenyl rings. Okay, somebody wants to join. Levofloxacin or oflofloxacin. So oflofloxacin, I don't remember if I have heard this name before, because levofloxacin is something which I have I think. So levofloxacin, actually it depends because of this levo, like we have say like R and S nomenclature, it is involved somehow in this molecule. As you can see, there is a double bond bold bond Me here. So due to this, it has this levo structure, and levo oflofloxacin, I don't remember her I mean this term, but there may be a structure also. Okay, so as we can see, there is this is the generic structure for the fluoroquinolones. Okay, so there are two rings present here, and as you can see, there is a ketone group and carboxylic acid group all together. Now this part, this is the SAR for this fluoroquinolones. Okay. So this is the SAR for the fluoroquinolones. So let us check out the SAR, how the SAR has been done on this kind of molecule. So as you can see, there is a ketone group here, there is a carboxylic group here, like as you can see, this structure and this structure are same, it is just drawn in a different manner. So this carbonyl carbon and this carboxylic acid group, these are the metal binding and chelation controls interaction with antacids, milk, iron and divalent cations. Okay, this R2 group, which is this at this position, no side effects is associated with this position, means we can just add any term in this position, or we can keep it vacant. This R1, which is this R1 means the bond with the nitrogen, this controls the theophylline interaction and genetic toxicity. Okay, and there is a this X8, it can be fluorine, chlorine, nitrogen, okay, or C8OMe, okay, and this position. Okay, so there can be a carbon, fluorine, carbon, chlorine, nitrogen, hydrogen or OMe. Okay, so this controls the phototoxicity. And this number 7, group number 7, it controls the GABA binding and theophylline interaction. There is a fluorine atom at the 6th position. As you can see, there is a fluorine atom in the 6th position, and this effect of this fluorine atom has not been yet reported. Okay, and influence of phototoxicity and genetic toxicity at this position of R5, and it can be greater than CH3, greater than H, greater than H2, and cardiotoxicity NH2 greater than CH3 greater than H. So, these are the group which can be tolerated here, or this the group which cannot be tolerated, it is mentioned here. So, that is how this actually in SAR what happened, we have this basic structure for a compound, okay, which is called the pharmacophore, and we have this kind of R1, R2, R3, all the functional groups present, and by changing each and every substituent we see how much effect does it impart on the final biological activity. Okay. So, that is how the SAR happens. So, this was the little bit out of the context question, but I think you guys also should know how the SARs are performed. Okay. So, now we will go to the problem. So, till now there is any question? Is there any question till now? Okay, I think it is clear. So, as I have always said, if you have any doubt, any query, please do write in the chat box. Okay. So, problem number 12, it says that which of the following statements is not true for the bacteriostatic agents. Okay. So, for the bacteriostatic agents, you have to identify which of the following statements is not true. The options are: number A, the agents stop the growth of the bacteria. Number B, the bacterial population remains the same. Number C, the agents destroy the bacteria. And number D, the agents inhibit the processes like replication, translation and transcription. You have to identify which of the following statements is not true for the bacteriostatic agents. Number A, the agents stop the growth of the bacteria. Number B, the agents population remains the same. Number C, the agents destroy the bacteria. Number D, the agents inhibit processes like replication, translation and transcription. So, always be careful with this true, false, true, not true type of questions, because these are sometimes very tricky. So, always read the options carefully, read the question carefully before answering it. Now, like always, I want everyone present in the class to try to answer this question. It does not matter your answer if it is correct or it is wrong, but try to answer it. Okay. Okay, so there any correct or there any answer? B is not true. B, number D. Okay, so we have B, and then we have I think D also, and we have also C. Okay, let us check. We have multiple answers for this question, like always. So, the correct answer is, or rather the untrue statement is number C, the agents destroy the bacteria. So, what is bacteriostatic and what is bactericidal? So, these two terms are very important and the comparisons are also very important. So, let us check out first the bacteriostatic. So, these and those antibiotics that stops or inhibit the growth of the bacteria, that means no multiplication or generation of bacteria, but they do not kill the bacteria. This slow their growth and reproduction, inhibits the DNA replication and protein synthesis of bacteria, work with the immune system of the host. Minimum drug concentration is required. For example, tetracyclines, penicillins, sulfonamides, linezolid, chloramphenicol, clindamycin and macrolides. These are the bacteriostatic antibiotic. So, there is another term which is known as the bactericidal. Okay. And what is the difference between bactericidal and bacteriostatic? The bactericidal refers to the antibiotic those kill the bacteria, but bacteriostatic refers to the antibiotic those prevent the growth of the bacteria. Okay. The action of the, okay, so wait a minute, I want to change something. There is Now I think it will be easier. Okay, so bactericidal refers to the antibiotics that kill the bacteria, but bacteriostatic refers to those which do not kill the bacteria, but they just inhibit the bacterial growth and prevent their growth. Okay, the action of bactericidal is the irreversible, but the action of bacteriostatic is reversible. The first one, they inhibit the cell wall formation of the bacteria, but bacteriostatic, they inhibit the DNA replication and protein synthesis of the bacteria. The first one, they do not work with the immune system of the host, but the bactericidal work with the immune system of the host to prevent the growth and the reproduction of the bacteria. The MBC refers to the concentration of the drug required to kill 99.99% of the bacterial population, but MIC is the minimum drug concentration which inhibits the bacterial growth. The examples include beta-lactam antibiotics, cephalosporins and vancomycin. These are the bactericidal antibiotics which directly kill the bacteria by inhibiting the cell wall synthesis, but tetracyclines, spectromycin, chloramphenicol, sulfonamide, these actually inhibit the bacterial growth or prevent the growth of the bacteria by inhibiting the DNA replication and protein synthesis of the bacteria. So, these were the differences between the bactericidal and bacteriostatics. Okay. And I also want you to remember the examples of the both of the kinds, how they work, and the basic differences. Okay, because this is a very important terms for the antibacterial agents, this bactericidal and bacteriostatic. So, I think, is it clear to all, or do I need to repeat anything? So, if you have any doubt, you can just tell me now. Okay, I think it is clear. Okay, so now we will move forward. So, the next question, it says that penicillins exert their antibacterial action by inhibiting the cell wall biosynthesis. Okay, which cell wall biosynthetic enzyme is inhibited here? Number A, carboxypeptidase. Number B, transpeptidase. Number C, glycosylase. And number D, phosphatase. You have to identify which of the following biosynthetic enzyme is inhibited by the action of the penicillins. And it is also the mechanism of action for the penicillin. Everybody present in the class, try to answer this question if you know, and if you think which is the this is the correct answer, try to write in the chat box. Okay. Which of the following cell wall biosynthetic enzyme is inhibited by the penicillins? Number A, carboxypeptidase. Number B, transpeptidase. Number C, glycolase. And number D, phosphatase. Okay, so have anybody tried to answer it? Okay, B, B and number C. So we have 2 number B and 1 number C. So let us check what is the correct answer. So the correct answer is number B, transpeptidase. Very good. Okay. So this is the mechanism of action for the beta. Sorry. This is the mechanism of action for the beta lactamase. Okay, that's a pointer. So beta lactam mechanism. So as you can see, this is the this is the cell wall for the bacteria, as you can see. Okay, so there is these are the terminal D-ALA bonds. Okay, and this is the PBP, transpeptidase unit. Okay, so and this transpeptidase units are actually catalyzes this cell wall biosynthesis. Okay, and this beta lactams, they bind to the transpeptidase active site. Okay, so as you can see, this is this enzyme, this brownish one, it is the transpeptidase subunit, and this beta lactams, they bind to this transpeptidase active site, and that's how this the enzyme is inhibited. And once this enzyme is inhibited, the block of the transpeptidase activity interrupts the cross linking of the cell wall synthesis. Okay, and that's how the cell wall synthesis is inhibited in the beta lactam antibiotic. Okay, so you don't need to remember all this mechanism in detail. Okay, how it is happening, after that which bond is formed or not, but remember the name of the enzyme and the thing that the penicillin exert their antibacterial action by inhibiting the cell wall biosynthesis. You try to remember these things. Okay. So now I will move toward the problem number 14. So problem number 14, it says that the 3 simple building blocks of the penicillin are number A, glycine, cysteine, valine, number B, alpha amino adipic acid, cysteine, leucine, number C, beta amino adipic acid, cysteine, isoleucine, and number D, alpha amino adipic acid, cysteine and valine. Identify which of the following are the 3 simple building block of the penicillin. Number A, glycine, cysteine and valine. Number B, alpha amino adipic acid, cysteine and leucine. Number C, beta amino adipic acid, cysteine and isoleucine. Number D, alpha amino adipic acid, cysteine and valine. Okay, so is there any answer? Okay, number C, number A, number C. So I think everybody should try to answer questions. Okay, so there are only 3 to 4 people who are answering, but I want everybody who are present try to answer the questions. Okay, it doesn't matter if your answer is wrong, because we are not here for any examination or anything, but you trying to answer the question is very important. Otherwise it won't be I won't be understand like you are listening the class properly or anything. That's why everybody try to answer the questions. Okay, let us check out the correct answer. So the correct answer is actually number D, alpha amino adipic acid, cysteine and valine. So this is the structure of the penicillin, right? Okay, let me use the laser pointer. So this is the structure of the penicillin. As I have shown you earlier, there is this beta lactam ring present, and fused with this there is this 5-member ring with the nitrogen and sulfur. This is a thiazolene kind of ring. Okay, and there is a carboxylic acid group here, there is 2 methyl group here and a amide bonding here. Okay, so L amino adipic acid or alpha amino adipic acid, L cysteine and D-valine. So, these three are the simple building blocks for the penicillins, and these three blocks are first joined and they are made in this ACV tripeptide. Okay. ACV means amino adipic acid, cysteine and valine. So, first the tripeptide is formed, and then what happened, this tripeptide is converted to the isopenicillinic N, and this isopenicillinic N gives rise to the cephalosporins and the penicillin G. Okay. So, this is the synthetic pathway. So, you do not need to remember the exact structures and this each and every structure of the isopenicillinic acid and tripeptides, but remember the names of the three three amino acids, the alpha amino adipic acid, cysteine and valine, because these three are important or simple building blocks for this complicated molecule of the penicillin. Okay. So, this was the problem number 14. So, now let us see the problem number 15. So, problem number 15, it says that which of the following statements is false regarding the gram positive bacteria. Number A, very much susceptible to antibiotics. Number B, they have low lipid content. Number C, peptidoglycan layer is thin and majorly single layered. Number D, outer membrane is not present. So, which of the following statement is false regarding the gram positive bacteria? Number A, very much susceptible to antibiotics. Number B, they have low lipid content. Number C, peptidoglycan layer is thin and majorly single layered. Number D, outer membrane is not present. Read the options carefully and find out which of the following is the false regarding gram positive bacteria. Okay, so do we have any answers for this question? Okay, so I think number D, number C, number D, number D. So we have 3 number D and 1 number C. Okay, so okay, let us check what is the correct answer. So the correct answer is number C. Peptidoglycan layer is thin and majorly single layered. This statement is false regarding the gram positive bacteria. Now, let us check out what is the differences between the gram positive and gram negative bacteria. So, the parameter, first parameter is cell wall. So, gram positive bacteria, the cell wall is a single layered and smooth cell wall. Okay. And for gram negative bacteria, this is the double layered and wavy cell line. Okay. Okay, one second. Positive bacteria. Okay. So, the cell wall is single layered and smooth for the gram positive and double layered and wavy for the gram negative. Cell wall thickness, the thickness of cell wall is up to 20 to 80 nanometers for the gram positive and 8 to 10 nanometer for the gram negative. Peptidoglycan layer, it is thick layer and also can be multi-layered, and for gram negative it is thin layer and often single layer. So, as you can see the number C statement, why it is wrong, because it is said that peptidoglycan layer is thin and majorly single layered for the gram positive, but actually for the gram positive the peptidoglycan layer is thick and can be multi-layered. The teichoic acid are present in the gram positive, but it is not present in the gram negative bacteria. Lipopolysaccharide is not present in the gram positive, but it is present in the gram negative bacteria. The outer membrane is not present for the gram positive bacteria. The outer membrane is mostly present in the gram negative bacteria. Lipid content is very low for the first one, but the lipid content is 20 to 30% for the gram negative bacteria. Resistant to antibiotics, these are very susceptible to antibiotics, and these are very resistant to antibiotics. Okay, so these were the differences. So is there any okay, so I think there was something wrong. So this is the comparison between the gram positive and gram negative bacteria. Okay, so this is the very important topic, the gram positive and gram negative bacteria. So if you can remember this few parameters and the example, the differences, it will be enough, I think. Okay, so this was all about the problem number 15. Now we will discuss the problem number 16. It says that which reaction is catalyzed by the beta lactamase enzyme? Number A, the final cross-linking reaction to form bacterial cell wall. Number B, the hydrolysis of the acyl side chain of penicillin. Number C, the hydrolysis of the 4-membered ring in penicillin. Number D, the biosynthesis of penicillin from LLD to LLD SCV. And SCV is the alpha amino adipic acid, cysteine and valine. Okay. So you have to identify which reaction is catalyzed by the beta lactamase enzyme, and I think I have discussed it earlier also. So now I want everybody to answer this question. Okay. Number A, the final cross-linking reaction to form bacterial cell wall. Number B, the hydrolysis of acyl side chain of penicillin. Number C, the hydrolysis of 4-membered ring in penicillin. And number D, the biosynthesis of penicillin from LLD SCV. Which reaction is catalyzed by beta lactamase enzyme? Do we have any answer for it? Yeah, this question is a little bit repeated. Okay. Number C. Okay, let us check out the answer. Yeah, the hydrolysis of the 4-membered ring in the penicillin is the reaction catalyzed by the beta lactamase enzyme. So yeah, we have seen this earlier also. Let us check it once more. So this is the beta lactamase enzyme. So this is the beta lactam ring. It is hydrolyzed by this beta lactamase, and this is the detailed mechanism as I have discussed. So there is a serine molecule present, and there is a base which abstracts this proton from this hydroxyl group of the serine, and this oxygen attacks this carbonyl carbon, and there is a negative charge delocalized on this carbonyl carbon. Then there is another base, and which actually takes up the proton from the oxygen, and then this ring breaks. Okay, and then there is a base 2, and this base 2 actually abstract proton from the water, and this water attacks to this serine attached carbonyl carbon, and after the hydrolysis we have this thing back. Okay. So this we actually discussed earlier also, but that time the options are little bit different. So here the options are little bit different, but you always remember the which is the correct mechanism pathway. Okay. Now let us go to the problem number 17. It says that IPN to 6-EPA conversion is done by number A, ACVS, number B, IPNS, number C, DAOCS, and number D, IPNA. All the full forms I will discuss later. So IPN is the isopenicillinic acid, and 6-APA is, I think we have discussed earlier, or we will discuss later. Okay. So this is actually this conversion takes place in the biosynthetic pathway for the penicillins. Okay. This IPN to 6-APA conversion, and these are the names of the enzymes. Okay. And this is, I think, ACV synthetase, IPN synthesis. Okay. IPNA and DSOCS. So, when we are discussing about the some this antibiotics, it is sometimes it is very required to know what is the biosynthetic pathway or what is the synthetic pathway for that particular enzymes. So, that particular antibacterial agents like the penicillin is a very important antibacterial agent. So, the biosynthetic pathway of penicillin, I think you should read it about, because this is very important, and this kind of questions can come to your exams also in terms of the big question, like write about the biosynthetic pathway of penicillins in detail. So, if you know, write the answer in the chat box. If you do not know, it is also correct, it is also fine, I will discuss it in detail. Okay, do we have any answer for it? Okay, which chemical we use to check the bacteria is gram positive, gram negative? If the stain is not there, it is considered a gram negative bacteria, ma'am. If the stain, okay, yeah, there is some stains, actually I don't remember the name, but there are some stains which actually used to detect if the bacteria is gram positive and gram negative. See, there are some differences in the cell walls of the gram positive and gram negative bacteria. Okay, in the peptidoglycan layers also, it can be multi-layer, it can be single layer. Okay, it can be I think there are some different components are present in the cell walls. So, based on that differences, there are some stains. I don't know, I don't remember the exact names of the stains which are used to stain, but there are some stains which are used for checking the if the bacteria is gram positive and gram negative. The stains actually are active in some gram positive either or gram negative. Okay, maybe it can stain the cell wall of either gram positive or either gram negative. So, that is why we actually check if it is gram positive and gram negative. Okay. Okay, let us now check the answer for problem number 17. So, the correct answer is number D, IPNA. So, this is the detailed biosynthetic pathway of the penicillin. Okay, I will just show you. So, this is the L-alpha amino adipic acid, there is L-cysteine and L-valine, and ACVS is the ACV synthetase. Okay, then this enzyme is used at first, and this enzyme what it does, it actually combines this three component, this three simple building blocks into the ACV, and the ACV, full form of ACV is the delta L alpha amino adipoyl L cystenyl D-valine. Okay, this is the ACV, and then there is the INPS, which is the IPN synthetase. Okay, and this IPN synthetase what it does, it converts that ACV to the IPN or isopenicillin N. Okay, and this isopenicillin N then converted to penicillin N by the IPN E. Okay, and then what happened, then this isopenicillin N can also be converted to 6-amino penicillinic acid, which is the 6-APA. 6-APA stands for 6-amino penicillinic acid. Okay, and this conversion is catalyzed by the IPNA or IPN amino hydrolase or IPN acyl transferase. Okay, this IPN can stand for the amino hydrolase or acyl transferase, both are the same, and this is this enzyme catalyzes the conversion of isopenicillin IPN to 6-APA or 6-amino penicillinic acid. Okay, and then what happens, like this 6-APA can be converted to other penicillins by this IPNA also. And then there is another enzyme IPNE, which is IPN epimerase, which converts isopenicillin N to penicillin N. Okay, and then penicillin N can be converted to deoxycephalosporin C or DAOC, and the enzyme which catalyzes this conversion is the DAOC synthetase or DAOCS. Okay, and this component can converts to other cephalosporin and cephamycins. So, this is very important biosynthetic pathway, because penicillins are very important class of the antibiotics, right. So, if you do not remember the structures of each and every component, it is fine, but remember the names, okay, like the ACV, IPN, what is DAOC, and what is the 6 APA, the full form of this all terms you should remember, and also remember the each and every enzymes which are involved for the conversion. The question can be asked like what is the enzyme which catalyzes the ACV to IPN conversion. The answer will be IPNase or IPN synthetase, okay, or the which is the enzyme which is involved in conversion of IPN to penicillin N, it will be IPN epimeradase, okay. So, this is the biosynthetic pathway of penicillin, and this was your problem number 17. Now, let us move toward the problem number 18. It says that erythromycin belongs to dash class of antibiotics. Your options are number A macrolide, number B tetracycline, number C oxalidione, and number D quinolone. So, you have to identify which of the following class of antibiotics where erythromycin belongs. Is it macrolide, tetracycline, oxalidione or quinolone? Okay, so do we have answer for this question? Number A. Yeah, yes, crystal violet stain. This is used for staining the bacterial walls of the gram positive and gram negative. I think if the gram positive bacteria have a very thick layer, so this crystal violet will absorb more, and it will be shown, I think, blue in under the microscope. Okay, I am not sure, but I think it is correct. Okay, so everyone think it is number A. So let us check. Yeah, the correct answer is number A macrolides. This is the structure of the erythromycin. So, as you can see, the structure is huge and there are so many carbons, and there is a very long, very core which contains 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 and 14 atoms. Okay. So, this is called the macrolides. Okay, what is the mechanism of action of the macrolides? So, erythromycin displays a bactericidal activity, okay, and particularly at higher concentration. So, we discussed what is the bactericidal. Bactericidal means it completely kills the bacteria, okay. It prevents the growth of bacteria by inhibiting their protein synthesis, okay, bactericidal, yeah. Erythromycin binds to the 23S RNA molecule in the 50S ribosomal subunit. These building blocks the 3 exit from growing peptide, thus inhibiting the translocation of peptide. So, as you can see here, it is the erythromycin inhibits the translocation. Okay. It binds to the 23S rRNA molecule in the 50S ribosomal subunit. So, this is the ribosomal subunit. This is a P side, there is a side. A side the tRNA binds. So, this is the position of the translocation, and this translocation is inhibited by this macromolecule erythromycin, so that the polypeptide chain cannot grow, okay, cannot grow. So, the protein synthesis is inhibited, and we had discussed like this same mechanism can also is followed by the molecule which is the tetracyclines, because the tetracyclines also they actually inhibit this protein synthesis, but they bind to the A side. Okay. So, based on the sites, you also want, I think you have to remember what are the particular antibiotics where they bind, and the mechanism of actions are very important. Okay. Now, we will go to the problem number 19, and it says that augmentin is a life saving drug, is a mixture of number A oxacillin and ampicillin, number B amoxicillin and clavulanic acid, number C oxacillin and clavulanic acid, and number D amoxicillin and pyruvic acid. Identify which is the correct mixture of the life saving drug augmentin. Okay, so do we have answer for it? Okay, so number B. Let us check out. Okay, yeah, very good. Number B, the augmentin is the life saving mixture of the of amoxicillin and clavulanic acid. Okay. So, this is the structure of the amoxicillin and it is a derivative of penicillin. As we can see, there is a beta lactam ring and the same structure of the penicillin. So, only differences in this position, and this is the structure of the clavulanic acid. Okay. And this is the augmentin tablet or augmentin drug. Okay. Now, the last question, problem number 20, it says that Merifil resin is number A chloroformylated polystyrene, number B chloroacetylate polystyrene, number C silicon dioxide, polymer of silicon dioxide which is SiO2 whole N, and number D polymethyl methacrylate. Okay. So, this Merifil resin, it is actually used in the solid phase peptide synthesis. Okay. And I think we have discussed the solid phase synthesis today itself, which is very much used in the combinatorial synthesis. Okay. And there are many resins which are used basically for the solid phase synthesis. Merifil resin is the one. So, you have to identify which of the following polymer is the used in the Merifil resin as a Merifil resin. Number A chloroformylated polystyrene, number B chloroacylated polystyrene, number C is SiO2 whole N, number D polymethyl methacrylate. Everybody should try to answer this last question. Which of the following is the Merifil resin? Number A chloroformylated polystyrene, number B chloroacylated polystyrene, number C SiO2 whole N, number D polymethyl methacrylate. Okay, so do we have any answer for it? Number D, number B, number A. So, I think we have 3 answers. So, the correct answer is number A chloroformylated polystyrene. So, this is polystyrene which is actually chloroform, and this is we have chloroformyl group present here. Okay, so solid phase peptide synthesis is very important. One technique of the solid phase synthesis. Okay, and Merifil resin is the mostly used resin for this solid as a solid support. So, what happened with the resin, we have this amino acid protective amino acid present. Okay. So, the first amino acid which is there is a free, this is the resin molecule, and we have a free NH2 group form of one amino acid and another amino acid. The NH is protected by this FMOC group, and we have what is the circle, first deprotection, then activation, then coupling. then cleavage and the peptide. So, first step is the coupling step. Okay, what happens, like there is a amide coupling and these are the reagents which are used like HBTU, HOBT, and these are the used for the amide coupling and this is a amide bond formation. Now, the second step is the deprotection of this EPMO group, which is used to done by 20% of piperidine DMF or in molecule in microwave for 4 minutes. So, this NH2 group is now I think this NH2 group is now cleaved and now free, and now then cleavage. And what is the cleavage? After the growth of a particular length of the polypeptide, trifluoroacetic acid is added and this group is attached from here, this resin is attached from here. Okay. So, the this is the resin, first the deprotection, then activation, then coupling and then cleavage. And when this EPMO group it is cleaved from this deprotected or cleaved from this molecule, this form a molecule which is actually light fluorescence active, and that is how we can check the progression of the reaction. Okay. So, this is all about solid phase peptide synthesis. So, now we have done with our today's session. So, here we discussed mostly about the antibacterial agents, about different antibacterial agents like penicillin, tetracyclines, macrolides, okay. And we also discussed the mechanism of actions of the all antibacterial agents. And always I want to say one thing, like for the antibacterial agents you do not need to actually know exact mechanism or the detailed mechanism, how the reaction happen, what are the reaction happen, but remember the things which is very brief mechanism of action, like tetracyclines, they inhibit the protein wall synthesis, like this kind of thing, or which antibiotic inhibits the actually the DNA synthesis. Okay. So, the mechanism of actions are very important, and also you have to remember the examples of the each and every classes of the antibiotics, okay, agents. So, these are the very important. So, this was the week number I think 9, and today we discussed the problems regarding your week 10. Okay. And next week we will discuss the problems related to your week 11 in the week 11, and then this material, this class material, the PPT and this video of today's class I will share with the NPTEL, they will share it to you, and I think it is clear. So, if you have any doubt or any query regarding today's class or regarding anything of the course, you can just drop a email to me. I will just share my email ID with you in the chat box. Okay. And if you have any query, you can just reach me out here, and in each and every class we actually discuss this week. So, we are going 1 week ahead, right. So, today it is week 9 session, but we have discussed the week 10 topics. So, after the week 11 session, when we will discuss the week 12 topics, we do not have anything left for discussing. So, in the last class, which will be the week 12 live session class. So, I want all of you to go through the materials very well and tell me the topics which you want me to repeat in the last class. Okay. I will prepare accordingly the slides. So, or if is there anything which you want to know extra out of the syllabus, you can also tell me that. So, from the next class I want all of you to tell me which are the topics we want me to repeat in the last class, in the live session number 12. Okay. I will prepare the slides accordingly. Yeah, I know remembering so many things are very difficult tasks, that is why you have to read it many times. Okay. Medicinal chemistry, the problem is there, the things are very important to understand, and also you have to remember the things, but it is very easy, you will I think handle it. But go through the materials we have covered till now, and tell me in the next class if you have some topics which you did not understand properly, you want me to repeat. So, I will repeat it at the last session, the week number 12 session. Okay. So, this is it today. We will meet in the next class in the next Saturday from 6 p.m. to this 8 p.m. Okay. And I will then stop today's session. So, thank you all for joining, and thank you all for answering, and I will hope like we will meet in the next session to discuss the next things. Okay. So, thank you. I am just closing the session for today.